What is the most mysterious thing you know? Maybe it's an unexplained urban legend in your hometown, or perhaps an internet rumor that you investigated thoroughly and never found an answer to. But today I need to share with you the greatest mystery I know. A mystery the size of the universe. Literally. The universe is expanding, and this expansion is accelerating. However, no one knows what causes this acceleration. The mysterious accelerated expansion of the universe is attributed to a type of energy called dark energy. And as far as we know, dark energy is just that. It is the energy that makes the universe expand faster and faster. And this energy is called dark energy precisely because it has never given us any indication of what its true nature is. And if you watch this video until the end, we will explore this mystery and understand everything we don't know about dark energy. We will see how Einstein discovered dark energy by accident, what the evidence and possible explanations for the greatest mystery of the universe are, and how, unintentionally, dark energy led to the greatest mistake in the history of physics.
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
The beginning of the 20th century was marked by revolutions in all areas of physics. This included the way we see the universe. In terms of observations, astronomers showed that our galaxy was not even close to being the only galaxy in the universe. The universe was much larger than we had imagined until then. And, on the theoretical side, Albert Einstein's general theory of relativity produced an equation called the Einstein field equation. The Einstein field equation describes gravity not as a force, which is what Newton's old equation described. In Einstein's version, gravity is the curve in the fabric of space-time. What this means in practice is that, according to Einstein's view, space itself is something that can change. In empty space, space is flat, smooth like a stretched fabric, and objects move in a straight line. If we place a massive object, the fabric curves. And this curvature is caused by the mass of the object on the fabric. Now, objects moving in the curved fabric do not follow straight lines, but rather curves that follow the distortion in the fabric. Similarly, objects moving near planets or stars are affected by the curve in space itself, which is perceived as gravity. The letter G on the left side of Einstein's equation represents this curve of space. And the letter T on the right side represents the distribution of matter that is causing this curve in space. The power of the Einstein field equation lies in how general it is. It is possible to start with the description of a curvature and find out what type of matter distribution causes this curvature, or start with a matter distribution and understand what it does to space. And it was precisely by combining the new observations of a universe full of galaxies with the Einstein field equation that allowed physicists to create something unprecedented, the field equation of the universe. And the idea behind this equation is simple. Based on astronomical observations of other galaxies, on the largest scales, the universe appears to be isotropic and uniform. Isotropic means that the universe appears to be the same in all directions. There is the same number of galaxies in all directions of the sky. Uniform means that there is no special place in the universe. All points in the universe are kind of the same thing, just in different places. All galaxies in the universe will see the universe the same way we do. The isotropy and uniformity of the universe are information about how its matter is distributed. And physicists like Alexander Friedmann put this information into the Einstein field equation to create and solve a single equation for the entire universe. And the result was shocking. The universe had a beginning. We are in the middle of its story, and one day the universe will have an end. This was shocking because, until then, the favorite position of astronomers was that the universe was eternal and immutable. And Friedmann's solutions challenged the view of an eternal universe upheld by figures like Albert Einstein himself. According to Albert Einstein, the universe was eternal and unchanging. According to Einstein's equation, the universe was finite and mutable. So, which of the two views is correct? Einstein wanted to be personally right, so he did something quite daring. Einstein changed this equation so that it agreed with him, adding a third term to the equation that he called the cosmological constant, which is this Greek letter lambda that was added to the equation. The constant had a very specific value, and solving Einstein's equation with it, the result was a static and eternal universe, as Einstein preferred. Within the equation, the cosmological constant functioned as a source of anti-gravity, preventing gravity from causing any kind of change in the universe over time. But here, I think it is important to make it clear that the true physical meaning of the new constant was not clear even to Einstein. He added the cosmological constant just to fix the universe and make it eternal. But Einstein's happiness did not last long. In the first half of the 20th century, observations of distant galaxies and radio waves from the remote past proved that the universe was expanding and that it had a beginning in a Big Bang more than 13 billion years ago. Einstein and his cosmological constant were wrong, and he even recanted, stating that the cosmological constant had been his greatest mistake. The question now is not whether the universe had a beginning, but rather what was the history that connected this beginning of our universe with the formation of galaxies that dominate the universe in the present. The general idea is that the Big Bang was the moment when the universe began to expand from a small region of space with extreme density and temperature. And with the expansion, the universe cooled and galaxies formed. The problem is that the observable universe is much larger than expected. Something caused the primordial universe to expand extremely rapidly, much faster than expected by Friedman's work and his equations of the universe. It was necessary to add something new to cosmology to explain the rapid expansion of the primordial universe. And not only that, this extreme expansion must have lost strength to allow galaxies to form. This new thing was called inflation. And the first version of inflation was proposed by Alan Guth in the early 1980s. The most popular idea of inflation is the following. The best description of the matter in the universe is through quantum fields. Quantum fields are like universal Excel spreadsheets. The value in each cell represents the energy that the field has in that region of space. And this energy, in general, is expressed as matter. When the electron field gains energy, it creates electrons. When electrons accelerate, they deposit part of their energy into the electromagnetic field, producing radiation, which are particles of light. And in this way, through the fields, the created matter interacts with more matter. When a field gains energy and does not produce matter, this energy manifests as pressure, like a gas trying to expand. And this pressure can give rise to an extremely rapid expansion of a primordial universe. That is, a quantum field full of energy would cause an expansion of the primordial universe, an inflation. Quantum fields have energy, and it is possible to place this inflationary field in Einstein's field equation. And this is where we find a strange coincidence. An inflationary field behaves exactly like Albert Einstein's cosmological constants. The pressure of an inflationary field acts against gravity, preventing collapses and creating the inflation of the primordial universe if it is intense enough. And if the inflation field did not lose all its energy after inflation ended, it would act exactly like dark energy, causing an acceleration of the expansion of the universe. The idea of inflation and inflationary fields is still hypothetical today. And it was even more hypothetical when it was first proposed. Evidence was needed for both inflation and dark energy. And this evidence came. In 1998, the High-Z supernova experiment studied the distance and speed from nearby galaxies to galaxies more than billions of light years away. And the experiment found a clear trend. The farther away a galaxy was from us, the faster it was moving away from us. In other words, the universe is expanding at an accelerated rate. Or, to be even more direct, there is some kind of unknown energy causing the accelerated expansion of the universe, which is exactly what we were looking for when we talked about dark energy. In other words, dark energy exists. And not only does it exist, but it behaves exactly like Einstein's cosmological constant. Einstein's greatest mistake was, in fact, an accidental success. Einstein only got the value of the constant wrong. And this brings us to the next point. What do we know about dark energy besides the fact that it exists? Dark energy is the dominant form of energy in the current universe, making up almost 70% of all the energy in the universe. The reason for this is that the amount of dark energy seems to be directly proportional to the volume of the universe. As the universe expands, the amount of matter remains the same, but its volume increases. Therefore, the density of matter in the universe decreases, but the same does not happen for dark energy. The density of dark energy is constant, and the amount of dark energy increases along with the total volume of the universe. The other thing we know is the density of dark energy in the universe, which is very low. For reference, 1 joule of energy is the energy that a weight of 100 grams held at a height of 1 meter has. The density of dark energy is 0.1 billionths of a joule per cubic meter. In other words, a 1-meter-sided cube of dark energy has basically the same energy as a grain of dust suspended in the air, which is very little energy. If you take all the dark energy that exists in the volume that the Earth occupies, which is more than 1 trillion cubic meters, you would have energy equivalent to a single gram of uranium, or 3% of the energy needed to power a commercial airplane. The density of dark energy is extremely low. But since dark energy occupies the entire universe with constant density, this low density accumulates and becomes the dominant factor in the modern universe. The larger the universe, the more dark energy it has, and the faster it expands. And that is precisely why most explanations of dark energy try to associate this energy with the vacuum of space itself, because the vacuum also increases with the universe. So, what are these possible explanations for dark energy? The first one is the idea I already mentioned, an inflationary quantum field. A quantum field that can store energy and act by creating an expansion pressure in the universe. Ideally, this dark energy field will be the same field that caused the accelerated expansion of the primordial universe. And dark energy will just be the late expression of this same primordial inflation. A more direct alternative is to try to associate the vacuum energy of space itself with dark energy. The universe is filled with quantum fields that generate matter as we know it. The energy of these fields is never perfectly zero. There are always small energy fluctuations happening due to the uncertainty principle of quantum mechanics. Because of this, the vacuum of space is not perfectly empty. There are always small fluctuations of energy appearing and disappearing in it. It's like a pond that, from a distance, seems perfectly smooth, but up close, has small ripples. The vacuum of space also has its ripples, and these fluctuations could give rise to the pressure of dark energy. The dark energy of the quantum vacuum is an excellent idea in theory. It explains dark energy without relying on something new, like an inflationary quantum field. The problem here is doing the math. It should be possible to predict how much dark energy exists based on quantum vacuum fluctuations. But when physicists did the calculation, it turned out wrong. Very wrong. This calculation is literally the biggest mistake in the history of theoretical physics. The observed density of dark energy in the universe is 0.1 billionths of a joule per cubic meter. The density predicted by the vacuum energy is 10 raised to the power of 110 joules per cubic meter. This is an error by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. An error of 1 trillion times. I said trillion 8 times, I think. So is there any third attempt for dark energy? More or less. There are some attempts to dismiss the existence of dark energy, but they are not so favored by the evidence. Currently, vacuum energy and inflationary quantum fields are our best candidates for dark energy. And to make matters worse, it is not impossible that dark energy is in fact both things at the same time. Perhaps both an inflationary quantum field and the vacuum energy of space contribute to the value of Einstein's cosmological constant. The mere existence of dark energy is already quite a problem, but the issue might be even more complex, requiring more than just a new theory to be fully explained. And if that doesn't satisfy you, that's the point. I said that dark energy was the greatest mystery of the universe. Dark energy is 70% of everything that exists, occupying the entire volume of the universe. There is dark energy around you at this moment, and you have no way of knowing anything about it, except for the fact that the accelerated expansion of the universe is its fault. And I don't know about you, but this makes me extremely uncomfortable. What do you think about the idea? Type here in the comments. And don't forget to subscribe to the channel. Thank you very much, and see you next time.